Okay, so when you picture two lines, you probably imagine them crossing at one single point, right? That's how most systems of linear equations work. But what happens when they don't? Today, we're going full-on detective and investigating the special cases, the systems where lines just refuse to play by the rules, leaving us with some pretty interesting mathematical mysteries.
So, before we can spot the culprits, we need to know what a normal, well-behaved system looks like. We gotta establish our baseline for a typical case.
And this is it, the classic scenario. You've got two different lines on a graph, and bam, they cross at exactly one spot. That single point? That's your solution, the one and only set of x and y values that makes both equations happy. It's clean, it's simple, and it's what we usually expect to find. But what if the lines decide to go rogue? What happens when they just refuse to cooperate and don't meet at that one neat little point? Well, this is where our investigation really kicks off. This brings us to our very first case file, the mystery of the parallel paths. We're talking about lines that are heading in the exact same direction, but are just destined never, ever to meet. All right, take a look at this system of equations. Now, if you're a sharp detective, you might spot a clue right away. See it? Both equations have the exact same slope, a slope of 2. That means they're rising at the same rate. So what do you think is going to happen when we try to find where they cross? And here's the evidence, laid out for all to see. On the left, you've got your visual proof. It's just two perfectly parallel lines that will run alongside each other into infinity, but will never ever touch. And on the right? That's our algebraic proof. When we try to set them equal to each other, we're basically forcing them to tell us where they meet. And this is what the algebra screams back at us. -5 = 1. I think we can all agree that's just nonsense, right? It's a total mathematical contradiction. This false statement is the smoking gun. It's the definitive clue telling us there is absolutely no value for x or y that could ever make these two equations true at the same time. It's impossible. So here's the key takeaway. When your algebra gives you a statement that's just flat out impossible, you haven't made a mistake. Nope. You've just discovered an inconsistent system. That's the official name for a system with no solution where the lines are parallel. Case number 1, closed. All right, one case down. Time to open our second file, the curious case of the same line. This is where things get even sneakier. The disguise is much better this time. Now, have a look at these two equations. Unlike our last case, these don't look all that similar at first glance. I mean, all the numbers are different. They look like two completely separate lines. But are they? Let's do some digging. We can use a technique called the elimination method to crack this one. So, watch this. What if we just take that entire first equation and multiply everything by -2? Maybe that'll help us cancel some things out when we put it next to the second equation. Let's see what happens. And there it is, the big reveal. Visually, when you actually graph these two equations, they land in the exact same spot. It's not two lines at all, it's just one. They were the same line all along, just wearing a clever disguise. And algebraically, well, when we do that elimination step, something just as weird happens. We get 0 = 0. Now, wait a minute. Unlike that impossible statement from our first case, this is, well, it's always true. 0 always equals 0. This is the algebraic signal that your two equations aren't just related, they're essentially identical. In fact, if you look closely, equation 2 is just equation 1 with everything multiplied by 2. This kind of case has its own special name too, a consistent dependent system. It's consistent because there are solutions, and it's dependent because the equations are basically just versions of each other. And since the lines are identical, every single point on that line is a solution, which means there are infinitely many solutions. Okay, so these are pretty cool mathematical quirks, for sure. But do these strange cases ever pop up in the real world? Or is this just stuff for a math textbook? Let's take a look at a practical example and find out. So check this out. We've got two plots of land here. One's a trapezoid, the other's a rectangle. We're given some formulas for their side lengths, and we know their total perimeters. Our mission, should we choose to accept it, is to find the values of x and y. Now, when we actually write out the math for the perimeter of each shape, this is the system of equations we get. At first glance, it just looks like a standard problem. But Given what we've just learned, do you spot any hidden relationship between these two equations?
Well, it turns out this is no standard problem at all. If you take that top equation and multiply the whole thing by 3, you get the bottom equation. Exactly. So when you try to solve it algebraically, you run right back into our old friend, 0 equals 0. And what does that mean? It means this real-world land problem has infinitely many solutions.
So we've cracked a couple of tough cases. What are the big takeaways? Let's do a final debrief and summarize the 3 and only 3 possible outcomes you can ever get when you're solving a system of 2 linear equations. All right, here it is. This is your ultimate field guide for any system of linear equations. It all comes down to the algebraic clue you find at the end. If you get a clear answer, like x equals 2 and y equals 3, you've got one solution. Your lines are intersecting. If you get a false statement, something impossible like -5 equals 1, you've found parallel lines with no solution. And if you get a statement that's always true, like 0 equals 0, you're just dealing with the same line in disguise, which means infinite solutions. Which brings us to one last little brain teaser. We proved that the land perimeter problem has an infinite number of mathematical solutions. But we're talking about physical plots of land here. Length can't be negative, right? So if we can only use positive, real-world answers, how does that change our conclusion about infinite solutions? It's a perfect example of how sometimes the real world adds one last fascinating twist to the math.